So 7.1, exploring exponential models. Exponential growth, as the value of x increases, y increases. Exponential growth is a very fast growth. It is not linear. It is not a straight line growth. It is one of the fastest types of growth there is. Growth factor is the constant percent increase. Certain things that grow exponentially, populations. It took considerably less amount of time to go from 5 billion people in the world to 6 billion people in the world. It has taken even less time to go from 6 to 7, 7 to 8, 8 to 9. It has gone from 8 to 9 billion people in your lifetime. Actually, it's gone, I think it's, yeah. We've gone from 8 billion people to 9 billion people in your lifetime. No, it's more than that. It grows exponentially. Everything does along those lines. Okay. Certain things we would like to grow exponentially are money, and it does. It's just because they're in the interest rates are such crap right now, it doesn't make much difference. Exponential decay is the value of x increases, y decreases. Decay factor is the constant percentage of decrease. It goes down by a certain percent every time. Half-life, radioactive half-life is exponential decay. Every certain period of time, depending upon what you're dealing with, half of it's gone. Half of the radioactivity is gone. And then half of that, then half of that, then half of that. You lose an awful lot right away, but you lose less the next time. And you lose even less the next time. Okay, it never quite actually technically goes away. Because if you're only taking half every time, you never get down to zero. For all intents and purposes, you get down to zero, but it never technically actually gets down to zero. That's the idea behind half-life. There are a few formulas. First one we don't use a whole lot in here, but it is basic exponential growth model. The second one we will use in here. In fact, I'm putting it up on the board right now, so that way I have it for later when we're doing some problems. Okay, the amount after a particular time period is equal to the amount we start with. For an investment, it's how much money we're investing. For population, it's the population we start with. And then it's 1 plus, or technically minus, the rate of growth or decay. If it's growth, it would be plus. If it's decay, it would be minus, because you're getting less. Raised to the time period. And this is a basic, an extremely basic exponential model. Very, very, very basic one. This is like an annual growth. It does so much annually. Okay, this is not how a lot of things work. This is just a very, very basic one. The one above is actually a little more realistic for most items, but a little more a little too complicated for what we're doing here. Okay. Today we're doing, in this class we do an introduction. We will use the basic one. So when you need, this one is the one that you need to know. You absolutely need to know this formula and its parts for this chapter. You will need to know that formula and its parts for the chapter test. Okay. Now, things start out pretty easy, actually. Example, determine the growth or decay factor. So if I have a 6% increase, how do I write 6% as a decimal? 0.06. So this is a 0.06 growth. Because it's an increase, it's a growth. 4% decrease. 0.04 decay. 28% increase. 0.28 growth, and 11.5 decrease, 0.115, and that would be a decay because it's going down each time. Starts out simple. We always start out easy at the beginning of every chapter. Do those. They're not there at all? Oh, okay. We'll copy them down. Okay, so this would be a 0.07 growth. And this would be a 0.13 decay. I just want to call my wife. 0.265 growth and a 0.32 decay. Fairly straightforward. Now, this one is a little trickier. This is your basic exponential model. And the idea is from this formula, from the equation, is it growth or is it decay? Yes. You know what? I think you missed the whole page. You missed the whole page. Okay, that's what happens. Okay, copy these problems down. Because you have the sample one, that's what happened. It missed the whole page and some other copies later. Yeah, I saw you on my list.
Oh, okay.
Go ahead and grab a seat. Okay, so once again, my apologies for not having this page in your notes. So determine if the equation represents growth or decay. This is actually not that difficult to do. The number in front is the amount that you start with. So we start with 2 of something. And then the number we raise to a power, that is our growth or decay factor. So this is what determines our growth or decay. If that number is more than 1, it's getting larger each time because I'm multiplying it by a number larger than 1. I'm going to have that much more of it. If it's a number less than 1, then it's going to be decay. This one's 0.5, which means I'm taking 0.5 every single time. I'm multiplying by 0.5 repeatedly, so I'm taking half each time. So this would be decay. And my decay factor would be 0.5. If it's less than 1, it's going down. Okay, because I'm taking half each time. Okay. This one here, it's more than 1. I'm taking 1.2 of it each time. I may start out with 0.8 of whatever I have, but I'm going to take 1.2 of that. So I'm going to take that 0.8 and add another 0.2 of that, another 20%. So this would be a growth. And my growth factor on this one would be 1.2. That's what we would go ahead and do the 1.2 on this. Going up that much each time. This one would be growth. And my growth factor would be 2. I'm doubling. I'm doubling every time. So every year my money doubles. That doesn't happen. Don't ever expect that. And so this one would be a decay. And 0.6 would be my factor because it's less than 1. I'm taking 60% each time. Okay. Now you have this page, so go ahead and you can do these. Are they growth or decay, and what is my growth or decay factor? Okay, so the first one would be growth. And the factor would be 5. You get 5 times the amount each time. That's quite a bit. This one would also be growth. And 2.8 is my growth on this one. This one would be decay. Because that is less than 1. 3 over 7. That's less than 1. And this one would also be decay. And that would be 0.3. 0.3. Questions on that? So we always start out simple. Don't worry, it gets harder.
Thank you.
You will need your calculators for this portion here. Even I don't do this one by hand. Numbers are too large. Remember, for exponents on your calculator key, on your calculator, you have a caret key. That's how you raise numbers to powers. Okay, so this is going to go to the formula from the front page that I wrote down over here on the board. How much after a particular time. We're doing a fairly simple version of this one. You're just plugging in the numbers here, calculating it to figure the final amount. So this is my initial amount, $10. This is my growth rate. This is my time t. Those are the parts that I need. So I start with $10, and I do one. Is it plus or minus? Is it going up or down? It's going up. So we do 1 plus, and then 5% written as a decimal, 1 plus 0.05. For how many years? 3 years. So that would be 10 times 1.05 cubed. And now remember, and this is where most mistakes are made, cube the 1.05 first and then multiply that times 10. Order of operations, exponents before multiplication. And after 3 years, you'll be making $11.58 because you're going to round off because your boss is nice. Maybe. 5% cost of living raise? That's actually pretty good. I like it. 5% cost of living raise. Questions? Okay. Same one on the next year. So I start out, my initial amount is $11,000. And then car costs $11,000, expected to depreciate by 12% each year. What is it worth in 7 years? Depreciation, is that going up or down? Growth or decay? Decay, depreciates. So that would be minus 0.12 for 7 years. So I get 11,000 times 1 minus 0.12 would be 0.88 to the 7th power. Yeah. So after 7 years, your car would be worth $44,495, and that's not necessarily an unreasonable thing. Cars do tend to depreciate very quickly, some more than others. Some hold their values better than others. Toyota trucks tend to hold their value for a long period of time. You will lose quite a bit right off the bat, but then they tend to hold steady for quite a while at a lower rate. So if you buy a new one, it will depreciate immediately, but once it goes down, it will hold its used car price for very high for a long time. Hondas are the same way. Okay. You have to do this to the 7th power first. Then multiply that times 11,000. Did you get it? Yeah. Otherwise, your calculator does exactly what you tell it to do. You said 11,000 times 0.88 to the 7th power, and it will do. It won't look at it as, because you're not doing it separately, it will do the multiplication in the order and then take that to the 7th power. You have to be very careful about how you type things in your calculator. Okay, next one, my initial amount is 500. And this would be interest, so this would be plus 0.032 to the 5th power. So 500 times 1.032 to the 5th power. And you can tell this is a dated problem because you will never make that kind of interest rate ever again. Banks no longer operate by that method. So at the end of 5 years, you had $593 and 84 cents.
Wait, hold on. So when you are like earning, why do you move the decimal 2 places?
Because you have to write a percent as a decimal. You always move it 2 places when you write a percent as a decimal.
Okay, and then it just depends on if it's earning or decreasing and which way you move it 2 places.
No, you always move it 2 places, whether it's plus or minus. Yeah, plus or minus is growth or decay. If it's growth, you add the rate. If it's decay, you subtract the rate.
Okay, but you still
always move it 2 places because you always, to make a percent of decimal, you move it 2 places. Yes, the years of earning 3.2% interest are gone. Does anybody know what a savings account pays now for interest? About 0.25%. Less than 1% interest rate is what they pay now on savings accounts. That's what they paid when I was your age. They don't pay that anymore. They stopped that model. Banks no longer make money by loaning and collecting money anymore. They all make money off of investing into stocks and bonds. So they don't give a crap. They don't pay good interest rates because they don't need to get your money. Used to be you'd give them their money for savings. They would loan that money out to somebody else. The other person would pay it back with interest, and then they would pass that interest on to you. That is no longer the model that the banks work on. They don't care. They don't have to pay you back because they take your money and they invest it, and they get it from other things other than this. They buy stocks and bonds. Okay, last one, 17,562. One, is this growth or decay?
Decay.
So it's minus 0.045 to the 7.5. Yeah, good luck doing the 7.5 power by hand. Well, I used to be able to do that, but we don't anymore because we're not,
We're devolving.
No, we're allowing technology to do the heavy lifting. But I get 12,433. Actually, 34 if you round off. Because you don't have 0.6 people. Questions?
Can you like write it out, like just like the whole thing, so I can just see every step?
Okay, so where'd this number come from? Yeah, that's our initial amount.
Yeah, I set up the whole thing.
Okay.
But I just
Put it in your calculator?
Yeah, but I got like I got this, which is like 0.70798.
Did you take that number times this, or did you multiply first? Because what you need to do is you need to do this part here, your rate, figure that out, and that was 0.955.
Oh, got it. Never mind.
Okay. Yeah. So you take that to the 7.5 power, then multiply it times what you started with. Order of operations. Do what's inside parentheses first, then apply the exponent, then do the multiplication. Okay, order of operations. Okay, your turn. Okay. So job pays $12 an hour, so it's 12 times 1 plus 0.04 to the 3rd power. So after 3 years, you will be earning $13.50 after rounding off. Next one, you invest 700, so you start with 700, and it's 1 plus 0.026 for 4 years. After 4 years, you will have $775.69, rounding off. And then the last one, the population increases, 52,311. 1 plus 0.035 for 5.5 years, and you will get 63,207 people. Rounding off because we don't have parking. Questions? Okay. Graphing using a table and the y-intercept. Okay, list the y-intercept. The y-intercept happens when x is 0. When x is 0, that means I have 2 to the 0. What is anything to the 0 power? 1. So my y-intercept is 1. My y-intercept will be 1. It will be 1 for either one of those. Okay. Now it says make a table and list the values, giving the y-intercept. Now I'm going to do a table of values. I'm going to do it horizontally, just because I have more room this way. -3, -2, -1, 0, 1, 2, and 3. And what I do is I plug all of those values one at a time into the equation. So I take 2 to the -3 power. The negative means it's 1 over 2 to the 3rd power, so I get 1/8. Put -2 in there, 2 to the -2 power. That's 1 over 2 squared, that's 1/4. 2 to the -1, that's 1 over 2. 2 to the 0, we already did that, that's 1. 2 to the first is 2, 2 squared is 4, 2 cubed is 8. Should not be that difficult to do. 2 to any power. Plot the points. And that is what exponential growth looks like. It starts out slow, but once it gets going, it goes in a hurry. And this is a doubling effect. I do double each time. This is growth. As I go continuously out to the left, and x gets smaller and smaller and smaller and smaller, what number do I approach? I approach 0. Is it ever actually 0? No. So I have a horizontal asymptote. It approaches the line, but never actually technically touches the line. It approaches 0. I only have an asymptote in one direction. I don't have one in the other direction. It never actually technically becomes 0. It becomes close enough that we really don't care about the difference between what it actually is and 0. It's close enough for government work. At some point, we say it just doesn't exist. But it's like a ways out there before we'll ever get to that. And then the next one. This is growth because I have 2 to the x power. The next one would be exponential decay because I have 1/2 to the x power. This one's a little more complicated. Still going to do the same thing. Set up a table, XY table. -3, -2, -1. 0, 1, 2, 3. And 0, 1, we already have. Let's actually start at the high powers and work our way down. Okay, so when I take 1/2 and cube it, that's 1 cubed over 2 cubed. So this is, 1/2 cubed. So this is 1/8. 1 cubed over 2 cubed over 2 cubed, 1 over 8. When I square 1/2, it's 1/2 squared, 1 squared over 2 squared. This is 1/4. This is 1/2, because anything to the first power is itself. The negative, what does that do? It takes a fraction and flips it over. So it takes all of those ones we've just done, and all it does is flip them over. So if 1/2 to the first is 1/2, 1/2 to the negative 1 is the inverse of that, or 2. To the negative 2 power would be 4. To the negative 3 power would be 8. And if you plot these points, that is exponential decay. Drops very, very quickly and then drops slowly, slower and slower and slower. So this would be half-life. I have half each time. Okay, I have 1/2 of what I had just a minute ago. So this is why something that is radioactive can be extremely dangerous. If your half-life is measured in tens of thousands of years, it will take 10,000 years for half of the radioactiveness to go away. Half of it. Which means it takes a long time till it is radioactively safe. On the other hand, you have certain elements, isotopes, whose radioactive half-life is measured in nanoseconds, which means almost immediately after its existence, it no longer is dangerous. It all depends upon the substance. Unfortunately, the stuff that we have stored in barrels in the mountains of Nevada is extremely dangerous. Okay, your turn. Make a table. Plot the points. Okay. So first one, x, y, -3, -2, -1, 0, 1, 2, 3. 4 to the -3 is 1 over 64. 4 to the -2 is 1 over 16. 4 to the -1 is 1/4. 4 to the 0 is 1. And then 4, 16, 64. So I have the point 0, 1, 1, 2, 3, 4. And then somewhere way up here. And then 1/4, 1/16, 1/64. And what happens is this one grows much, much faster than 2 to the x. This one's a little more complicated. 3, -2, -1, 0, 1, 2, 3. Because I have to take 1/4 to that power, then multiply that number times 2. So for example, my y-intercept when x is 0, 1/4 to the 0 is 1, but I multiply that times 2, I get 2. Everything is shifted up. Okay, instead of going through the point 0, 1, it goes to the point 0, 2. And so then I have 1/4. So take 1/4 to the first power, it's 1/4 times 2. This is actually 1/2. Um, 1/4 squared is 1/16 times 2 is actually 1/8. And then 1/4 cubed is 1/64 times 2 is actually 1/32. And then these are all basically the inverse of that. So that's 4. Actually, it's not quite the inverse of that. So I take 1/4 to the -1 power is 4 times 2 gives me 8. 1/4 to the -2 is 16 times 2 is 32. 1/4 to the -3 power is 64. Times 2 is 128. So you can see that it really grows something fierce. It does not drop quite as steep, but still drops pretty steep. Okay, and that's what it should look like. The main thing that you need to understand when you're looking at growth and decay, what does the basic graph look like? If I've got growth, it starts out really slow and then boom, shoots up in a hurry. If I've got decay, it comes down really fast, but then goes shallow and stays shallow for a long time. You have to understand the basics of what these graphs look like. The larger the number, the bigger it grows, the faster it decays. If I multiply times the number out in front, what does that do? That shifts it up. Questions? Okay, normally we would be done with everything in your notes, but I changed your notes. Normally the next page would be a summary. I have added to your note packets. Okay. You will notice there are a couple of pages of what I am now calling independent work. These are more sample problems, just like what we got done doing. No, you're sticking out lesson quizzes. Okay. These will need to also be completed when your note packs are collected at the end of the chapter. If this isn't done, you don't get full credit. And your note packets, because of this added work, are going to be worth more points. So right now, they're worth, generally speaking, 40 points. This will add another 20 points to the packets, because you're going to have problems at the end of every section that you need to get done. I strongly recommend you work on them while you have time to work on them in class.